Thank you for giving me first this chance to talk to you today about my work in tunneling magnetoresistance sensor devices with magnetically engineered amorphous free layer. So actually first regarding to the TMR sensor. TMR
Mohammed,
sensor.
yes, so can you please share your, put it on the full screen?
Yeah, sorry.
All right, thank you.
Okay, so the kind of magnetic tunnel junction is a kind of magnetic element consisting from two ferromagnetic layers, as you can see here. One is the reference layer, second is the sensing or the free layer, insulating by an insulation or oxide layer. Actually, the situation is that when you have a magnetization configuration is parallel to each other, then you will have a very low resistance, we call R minimum, and when the direction of magnetization of these two magnetic layers are anti-parallel, then you have a high resistance we call R maximum. The point in this case actually is that the transformation between these two resistance state or these two magnetic state is happen abruptly or switching suddenly like this. So consider the positive and negative sweep, you will get kind of squared hysteresis loop. And in this conventional magnetic tunnel junction, I mean, when there is a parallel direction of magnetization, you can't use this conventional MTG as a magnetic sensor. On the other hand, here, in order to use a magnetic tunnel junction as a magnetic sensor, then the transformation between R maximum and to R minimum and vice versa should go linearly like this, and we call coherent rotation of the magnetization of the sensing layer with the reference layer. And only you will get this kind of very linear transfer curve or hysteresis-free curve if the magnetization direction of the reference layer is orthogonal to the sensing layer. Actually, there are a lot of strategy or linearization technique reported in literature in order to get this kind of linear transfer curve. For me, actually, I personally like two-step annealing technique in order to get this kind of linear transfer curve. And this is simply because it's produce a very, very linear and hysteresis-free curve. It's mean very low noise sensor you can produce. But it's need to some tricky point regarding to the annealing, regarding to microfabrication, and I'm gonna to talk about them one by one. Firstly, let's start with the annealing techniques. So generally, you need to anneal your layer structure at high temperature, like 300 or more, in order to crystallize MgO. And because of this annealing, then you will get parallel anisotropy. It's mean sensing layer magnetization and the reference layer magnetization are paired to each other. In the second annealing step, all what you will do is to rotate your device inside the magnetic field and lower the annealing temperature to a temperature equivalent to the blocking temperature of the iridium manganese or antiferromagnetic layer. Then it will lead to reverse direction of the sensing layer like this, perpendicular to the sensing layer magnetization. This is a very simple description for this technique, and when you get this kind of magnetization configuration, you will of course generate this kind of linear transformation curve. So regarding to the problem statement, so what is the problem statement? The problem statement is very clear and very known from 2012. It's written by Ricardo Ferreira in this article. Actually, he said actually people usually couple ion boron. It's in the free layer with a thick layer of nickel ion in order to enhance and control the soft magnetic properties of the free layer. The problem happened because of this coupling. Actually, it's totally material preparation or material issue, because nickel ion, it has a fast intercubic 1-1 texture, and in order you get the high TMR ratio, or order you get a high response from the sensor, then MgO must acquire 001 texture out of plane in order to improve the tunneling property across the barrier. So because of that, then this kind of lattice mismatch as the interface here it's produce a kind of strain effect or interfacial effect. It's work as an electronic noise at the interface here. This is the reason why the TMR ratio decreases. Another point, when you anneal your layer structure at high temperature, like 300 or 350 for crystallization, then the soft magnetic properties of the nickel ion started to degrade. And because of this degradation, it appears like hysteresis. And once hysteresis appear, then the noise increases. You can't use sensor as or MTJ as a sensor, as a good sensor. So the first goal of this presentation is to enhance the magnetic and the tunneling and sensing properties of TMR ratio of TMR sensor devices with no influence on the texture of cobalt ion boron sensing layer. How we can do this, instead of using the crystalline nickel iron, we will simply remove it and replace it by amorphous phase of cobalt iron boron tantalum. Exactly what we will do is take this one and introduce some tantalum, and then we will produce soft magnetic material, but without template. So as you can see here, I'm showing to you the layer structure that we schematic that we developed at NIMS. Actually, it consists from 20 nanometer cobalt ion boron tantalum. Above it, this cobalt ion boron. This then we can consider this one as our sensing layer with high or with very good soft magnetic characteristic. This is the only point is that we only replace this one by instead of using nickel iron, we just use this one as amorphous soft magnetic layer. But the tricky point, as I mentioned at the beginning of my discussion, to fabricate the sensor is that when we etched the pillar, we stopped our etching at the interface between MgO and the free layer, exactly stopped around this interface. And this is because we need to reduce the chip anisotropy effect. We didn't etch actually the free layer, we kept it flat in order to reduce the shape anisotropy effect and make the magnetization in the free layer is only controlled by induced anisotropic magnetic anisotropy, which produced during magnetic annealing. Okay, anyway, this is observation of this layer structure by electron microscope. And as you can see here, this is a free layer, is still amorphous even if we anneal this layer structure around 350 degrees Celsius. It means there is no influence on the cobalt ion boron, and so we can get high TMR ratio, we can get hysteresis-free curve. This I'm sharing with you here. The black curve is the hysteresis or the curve after the first annealing, and after the second annealing, you can see this is almost hysteresis-free curve, very close and very linear, so it can work as a very good magnetic sensor. Actually, after that, we started to study the thickness dependence of the CFPT free layer. We just increased from 20, 40, 60, and 80 nanometer. We are looking forward to increase the soft magnetic properties of the free layer, but unfortunately, because of increasing this thickness, we found that the roughness of the surface started to increase, and because of this, as you can see here, the TMR ratio decreased, and so the sensor sensitivity started to decrease. So we fixed 20 nanometer, this one, 20 nanometer CFPT thickness is our superior as a magnetic free layer. After that, we went to the noise measurement. We put our sensor as a central of Helmholtz coil inside a 3-layer permalloy shielding chamber. We bias our device using a battery box, and then the output signal amplified before going to the signal analyzer for FTT analysis. And actually, we bias our device by 1 millitesla in order to bring the intermediate state of magnetization, where the sensor works as a magnetic sensor, where the MTJ works as a magnetic sensor during this region. And we started to increase the bias voltage. And as you can see here, normally as we increase the bias voltage, then the noise voltage increase, as you can see here. And from this measurement, we picked the value of the noise voltage for 30 millivolts, and we calculated the magnetic field detectivity. We got 2.2 nanotesla per root hertz square, which is much more better than that reported by the magnetic sensor developed by nickel iron copper iron boron free layer. After we achieved this in 2021, actually, we become too motivated, and the plan for our next step. Actually, as you can see here, this is our hysteresis-free curve. But if you can look deeply to this linear transfer curve, you will observe that delta H is a little bit wide. So the point is, if we can successfully decrease this delta H is determined how much sensitivity you have. So if we can decrease this delta H value, for example, from 2.5 to 1.5, for example, then the sensitivity starts to increase. Coming back to this literature or this paper from 2002, it's been 20 years ago, actually. These two guys, Professor Gang at Brown University and Parkin at IBM at this moment, they said that the nickel iron has the smallest delta H among other soft magnetic material. So what came in our mind is to couple between the soft magnetic properties of our new regenerated or newly proposed CFPT in the first part of my talk, together with nickel iron in one pi layer, and introduce in the stack structure and use that as a free layer, new free layer. And this is our topping MTG. This is how we suggested for free layer new design. For example, this is CFT, just a 20 nanometer. We coupled it by 5 nanometer nickel iron, and then 10, 20. And we also compare with 20 nanometer nickel iron. And then we started to do, again, two-step magnetic annealing technique. And I'm sharing with you here the result of this is the result of the magnetic properties from the thin film, very linear curve, as you can see. And as you can see here, we can successfully reduce delta H. This is from the magnetic thin film. Same result we got from the TMR curve after microfabricated devices. And the same, actually, as you can see here, successfully reduce a delta H. And because of this, we can successfully duplicate or increase sensor sensitivity from 70% per millitesla to over than 110% per millitesla. And so the detectivity improved to 1.5 nanotesla per root hertz square. So in conclusion, actually, we have achieved the minimum magnetic field activity around 1.5 nanotesla per root hertz as at 10 hertz, which is promising and more sensitive than previously reported through literature. So thank you so much for listening and attending my presentation. Any question, please?
All right, thank you, Mahmoud. The floor is open for questions. Please feel free to raise your hand or type in the chat box.